So let's start again. So after seeing how to correctly use a random number generator, now we will see how to sample from a distribution. So the problem here is that we have a distribution f, and we know how to sample from the uniform distribution between 0 and 1. So this is done by the random number generator. And we want to produce a sample from the random variable x that is drawn from the distribution f. And this is a very common task in simulation. Usually we will have MATLAB to do it for us. So there are already functions developed that we can use to draw samples from several distributions, but sometimes this may not be possible. And we will describe now, we will learn now two methods to do this. The first one is the cumulative distribution function inversion, which is actually an analytic one. And then we have rejection sampling, which is it's more sampling, it's more numerical. And we'll see these methods now. The CDF inversion first applies to both real and integer valued random variables and works as follows. First, we draw a sample u from the uniform distribution between 0 and 1. And this is done using the random number generator. This is done for us by the random number generator. Then we take the inverse of the CDF that we have, f inverse here, and we evaluate it at u, where u we have obtained from the random number generator. And this gives us a sample of x, where x is a random variable that follows the distribution f. Okay? Let's see it now graphically. So we have u here that it's drawn by the random number generator. Is between 0 and 1 because it's drawn from the uniform distribution between 0 and 1. And the CDF that we want to create a sample from it is this one. So we have u here. We put it on the y-axis, which is between 0 and 1, because this is a probability. So we put it in the y-axis. And then we have that f of x should be equal to u. And then we solve for x by taking the inverse of f, and it will be here. Okay? So we take this x value here as a sample from the random variable that follows the distribution f using a random number generator. Let's see the proof of it. So what we want to prove is that the x that we have obtained has a distribution, a CDF equal to f of x. So we want to find this probability, that the probability of x less or equal to x small is equal to f of x small. Okay, we want to prove this. So first we have that u is uniformly distributed, therefore this is true. So the probability that u is less or equal than u small is equal to u for every u that is between 0 and 1, because u is uniformly distributed. Then we know that we have defined x equal to f inverse evaluated at u. Therefore, u is equal to f of x, okay, taking the synthesis with f. And then, since f is a CDF, it is monotonic increasing. Therefore, if we have an inequality here, x less or equal than x small, we take the synthesis with f, the sense of the inequality doesn't change. So the inequality is kept the same. Therefore, in order to compute this probability of x less or equal than x small, we take the synthesis inside with f. So this is, we have equality here. And then since this here is equal to u, we apply this relation. And instead of u small, we have f of x small. And this is equal to f of x small. Okay? So we have proven that CDF inversion gives gives a sample of x that follows the distribution f, and we have just shown that x has a distribution f. Okay? Any questions on that? No. So let's apply now the CDF inversion for an exponential random variable. The CDF of an exponential distribution is with parameter lambda is this one. In order to find now the inverse, we just set this equal to p, and we solve for x. Okay? So the solution with respect to x will be this one here. Then what we said before is that we take the inverse and we evaluate it at u, where u is created by the random number generator. So we have u that is given to us by the random number generator, and we put it instead of p here. Okay? And because now u and 1 minus u have the same distribution, because u follows the uniform distribution, so 1 minus u will also follow the uniform distribution, so they are both the same. In order to simplify this expression, instead of 1 minus u, we just put u here. And this relation here gives us a sample from the exponential distribution by knowing a sample from the uniform distribution between 0 and 1 given by a random number generator. Okay? So any questions? Okay, move on. Now, as we said before, the CDF inversion applies both to real valued random variables, but also to integer valued random variables. In order now to apply it for integer valued random variables, we will first define the pseudo-inverse. The pseudo-inverse is defined for both for real valued random variables and integer valued random variables, but we will just define it because it's needed. Yes. Now, in order to define, so assume that f is the CDF of a random variable x, which has values in the real numbers, takes values in the real numbers. Then the pseudo-inverse is defined by this relation, so at p. So it's equal to the supremum of x, such that f of x is less or equal than p. Okay, so this is the pseudo-inverse of f evaluated at p. And this is actually the pseudo-inverse for a distribution with jumps, which is needed in order to define in order to apply the CDF inversion for integer valued random variables, because in integer valued random variables the CDF will have jumps. Okay, as we see here. So these are jumps. And then, as we did before, we have u that is given by the random number generator, a sample from the uniform distribution between 0 and 1. And we just evaluate the pseudo-inverse at u. So we set, we have p, we set u, and this is a sample of the random variable x that follows the distribution f, that is a distribution with jumps. Okay? And now we will see how we'll apply this to integer valued random variables. So we will try to apply this theorem here. So we want now to draw a sample of the random integer n, for which we have this probability density function. So pk is equal to the probability that n is equal to k. And this is the cumulative distribution function. So fn equals to the sum of pi for I from 0 to n. Okay? F minus 1 equals to 0. So it's higher than 0, higher or equal than 0, n. And then in order to apply this, we first find the pseudo-inverse. Okay? So we obtain the smallest integer n such that p is strictly less than f of n. We will see it here in the figure. Sorry, I will go a little bit back and forth in these slides. So we have p that is here. We want to evaluate the pseudo-inverse at p. To compute the pseudo-inverse at p, we find n such that f of n is strictly higher than p. So in this case is this here, this n here. Okay? So this is strictly higher than p. Then for any value in the set from minus infinity to n, where n is open here, so without n, but this set, so minus infinity up to n, this set here is equal to this set without the supremum, to this set here. So it's x, all x, such that f of x is smaller or equal than p. Okay, because we see here that fn minus 1 is less than p. Okay, so for any value up to here, the CDF is less than p. Okay, so this set is here, is this one. So the supremum of this set is equal to n. And since the supremum of this set is equal to n, the pseudo-inverse of f evaluated at p is equal to n. Okay, so in order to simplify this, the method is this one. So we draw, this is the explanation, we draw a u from the uniform distribution between 0 and 1 using the random number generator. And then we take the output, the random sample of the random variable we want, the integer random variable we want is n, such that u is strictly less than f of n and higher or equal than fn minus 1. Okay? And we can see it also in the figure. So we draw, let's assume that this is u. We obtain the random sample of the integer valued random variable n is n, where f of n is strictly equal than p, and f of n minus 1 is higher or equal, and p u is higher or equal than f of n minus 1. Sorry. Okay? Any questions here? It's quite difficult, but we will do an example now. So assume that we have a random integer n with values between 0 and 9, and it's uniformly distributed between these values. So its value appears with probability 1 over 10, okay, 0.1. So the cumulative distribution function will be this one. F minus 1 will be equal to 0 because it starts taking values from 0. F0 will be 0.1, F1 0.2, and we arrive at F9 will be equal to 1. Okay? So first we try to apply the method before. So first we draw u using the random number generator from the uniform distribution between 0 and 1. Assume that u is equal to 0.22. Okay? Then we need to find n such that f of n is strictly higher than u. So we go here. We need to find the smaller such n. So we go here, and this is 2, f2, so n is 2. And f of n minus 1 is higher or u is higher or equal than f of n minus 1, so u is between the two. So the output will be 2, okay? Be the higher of the two. So if u is equal to 0.78 now, then we need to find n minus 1 and n such that u is in between practically. So it will be here between 0.7 and 0.8, and we return this. We return the highest. So we return 7. So the sample of the random integer will be equal to 7. Okay? So any questions? Now this was a simple distribution. We probably want to apply it for a Poisson, let's say, distribution with a cumulative distribution function given by this formula. So we draw u using the random number generator, and then we return n such that fn minus 1 is less or equal than u, which is less than f of n. Okay? And for this we need to compute for different n and find which n is the correct one, because there's no closed form formula. Okay? We will see now another distribution for which there is a closed form formula, the geometric distribution with parameter theta. And here we have that x is an integer random variable and takes integer values higher or equal than 0. The geometric distribution has this probability density function with parameter theta. And the probability, the cumulative distribution function is this one. Okay, so it has this form. So we try to apply in this equation, we try to find the pseudo-inverse of f at p, evaluated at p. So for this we apply this relation here. And if we do some trivial calculations on this relation, we will end up with this. Okay? So this, we see that the n we want, the sample of x, is obtained if we take the floor of this quantity. So we have a closed form formula now for the pseudo-inverse evaluated at p. Okay, and as we said before, in the pseudo-inverse we should evaluate it at u, where u is given by the random number generator. So instead of having p here, we will have u, and because u and 1 minus u have the same distribution, this can be simplified to this relation here, and this gives us a sample of the random integer x. Okay? Any questions? This? No. Okay, so a question for you then. So what does this function compute? My function p, if the random number generator is less than p, return 0, otherwise return 1. And all of you that answered correctly. So the answer is B, but we will see why. So it's the flip of a coin where 1 is obtained with probability 1 minus p and 0 with probability p. So the flip of a coin that returns 0 with probability p and 1 with probability 1 minus p, because it has two possible results, has this CDF. So f minus 1 is 0, f0 is p, and then f1 is 1 minus p plus p equal to 1. Okay? So we will apply this relation again. So we take u from the random number generator, and if u is between f minus 1 and f0, so it's between here, between these two, we will return 0. We'll return the highest, okay? 0. If u is between p, f0, which is p, and 1, we will return the highest, we will return 1. Okay? So practically when u is less than p, strictly less than p, we return 0. And if u is from p to 1, we'll return 1. So else we return 1. Okay? So this algorithm is the flip of a coin that returns 0 with probability p. Okay, any questions? Okay. So another question for you. So which one is a uniform random point? The answer is B, so all of you replied correctly on this. And let's see the why. So A is regular, there is no randomness at all. Okay. And B is random and it's sampled from the uniform distribution, so this is a uniform random point. Okay. This was simple. So let's see now how do we sample a uniform point in a rectangle. Assume that we have a rectangle between x min and x max, so the x-axis, and y min, y max is the y-axis. Okay. And first we check if x and y are independent. So we see that the distribution of y, given that x is equal to x small, is again uniform between y min and y max. Therefore, it does not depend on x small. Therefore, they're independent, both of them. Okay. So how do we do it? So how do we create a sample here, a uniform sample, a uniform point? We draw u and v from the random number generator. So u and v are independently drawn from the uniform distribution between 0 and 1. But then they are between 0 and 1. So what we want is x to be between x min and x max, and y to be between y min and y max. So we need to rescale u and v, okay, to obtain x and y. So in order to do this, we scale u, and we practically do x min plus u multiplied by x max minus x min. What I said here is this relation here. So we have a random number u from the uniform distribution between 0 and 1, and we bring it between x min and x max. And then we have a random sample for the x coordinate x. Okay? And then v is again between 0 and 1. So we bring it now between y min and y max, and we have a sample for the y axis, for the y coordinate. So we have this uniform point x and y, okay, in the rectangle with the given coordinates, with the given side lengths. Okay, any questions on this? No, simple. Okay, let's now see another question for you. So we sample a point M uniformly in some arbitrary area. Are X and Y independent? Basically, for this area here, they are not, but for the square that for the rectangle, sorry, that we saw before, they were independent. So the answer is yes, because as we said, the distribution of y, given that x is equal to x small, is uniform between y min and y max. So does not depend on x small. So they were does not depend on x. So they were independent. Okay, but for this area here, they're not, because if we take x equal to -5. Then y is uniformly distributed between 0 and 20. Whereas if we take x equal to 5, then y is uniformly distributed between -20 and 40. So the distribution of y depends on x, therefore they're not independent. Okay? So what is the PDF of the uniform distribution in this area A? So the uniform distribution has a constant probability density function, but it will not be, it has a constant probability density function in the area A and 0 outside, okay? But it will not be 1, because this constant normally is determined such that the total probability is equal to 1, okay? So we should, if we integrate this for all the area A, it should be equal to 1. So this constant is equal to 1 over the area A for any point that belongs in the area A and 0 otherwise. Okay, so the answer was C, something else. Okay, let's move on. Again, another question. How can we sample a point uniformly distributed in this area A? So first, the A draws x from the uniform distribution between -10 and 20, and then draws y if x is between 0 and 10. So it's here. It draws y from the uniform distribution between -20 and 40. Otherwise from the uniform distribution between 0 and 20. But this is not correct, because x is not uniformly distributed between -10 and 20. Because if you see here, it has higher chances of falling between 0 and 10. Because if we have a uniform distribution in the area A, there we have more points than we have here and here. So x has higher chances of falling between 0 and 10. Okay, so this is not correct, that we draw x and then depending on x we choose for y, sorry. Then B draws x from the uniform distribution between -10 and 20, and then y from the uniform distribution between -20 and 40, and then performs a test and checks if the point it has drawn belongs in the area A or not. So it draws uniformly a uniform point in the rectangle here, and then if it performs a test, if this point belongs in the area A, it keeps it, it returns it. Otherwise, it rejects the point and draws another point. Okay, this is the correct one, and this is called rejection sampling, as we will see. And this is the second method for drawing a sample from a distribution. So this algorithm B produces a sample of the conditional distribution of x, y, given that x, y belongs in the area A. Okay, we will see this later in the theory. Let's see the probability, the distribution now that B algorithm gives. Okay, so we compute the probability that x belongs between x small and x and dx, and y between y and dx, given that x, y belong in the area A. Okay, so this is equal to, this is a conditional probability and is equal to the cut of the two probabilities of this one and x, y belong in the area A over the probability that x, y belong in the area A. Okay, this is just a simple probability formulas. And then this one the probability that x belongs here and y belongs here is equal to dx multiplied by dy over the whole rectangle, okay, because we draw them uniform in the whole rectangle. Then the probability that x comma y belongs in A is given by this here, 1 when x comma y belongs in A and 0 otherwise. And this probability here is equal to the area of A over the area of the whole rectangle. So the area of the whole rectangle goes away. So we have this result here, and the probability density function is this one. Okay, so it's this one. So the probability density function that algorithm B gives is the correct one, is the uniform distribution in the area A. Okay, so it is equal to 1 over the area A if x comma y belong in the area A, and otherwise 0, as we've seen before. Okay, because if you remember in the previous question. So algorithm B gives the correct probability density function. Okay, now we will see, if you don't have any questions, we will see the theorem for the rejection sampling for the conditional distribution. So assume that we have x that is a random variable, and the distribution of x is equal to the conditional distribution of x tilde, given that y tilde belongs in A. So we see now the theorem. Then we obtain a sample of x as follows. We first draw a sample of x tilde and y tilde until y tilde belongs in A. Then we return x tilde. So if y tilde does not belong in A, we repeat. We draw another sample of x tilde and y tilde. And we will see now how this theorem maps to our previous example. The expected number of iterations until we finally have a sample of x is equal to 1 over the probability that y tilde belongs in the area A. Okay. So in the previous example, we first draw a sample of x and y uniformly in the rectangle. Okay. So here in the theorem, this is x tilde. This corresponds to x tilde. So x tilde corresponds to x comma y that are uniformly distributed in the rectangle, and y tilde the same, because we check if x comma y belong in the area A. So y tilde corresponds also to x comma y uniformly distributed in the rectangle. And then what we obtain at the end is a sample of x, and we obtain x comma y that follows the uniform distribution in the area A. Okay, so that is the mapping with the previous example. We'll see it also now. So what we did before is we sample a point x comma y uniformly in the rectangle, which is a bounding box around the area A, from where we want to obtain a random sample uniformly. So we first have a bounding box around the area A, and we sample uniformly in this bounding box a point. And then we check if this point belongs in the area A. If yes, we return it. Otherwise, we repeat the process. Okay, we reject it and we repeat the sampling. So if we see, if we see here the correspondence with the theorem, we draw a sample of x tilde, y tilde. We draw a sample of a point x comma y. So both y tilde and x tilde are the same, and are x and y that are uniformly distributed in the rectangle. And we check. If y tilde belongs in A. So here we check if x comma y, because this is y tilde, belongs in A. If it's not in A, we repeat and we reject and we repeat. Otherwise, we keep it and we return it. Okay, so this is rejection sampling. So we should note that the distribution here is uniform in the rectangle, in the whole rectangle, whereas the distribution of the point we obtain at the end is, as we saw, is uniform in this area A. So the distribution of the point here is not the same as the distribution of the point here, because we sample a point uniformly in the rectangle, which is a bounding box around the area we want, and then we reject it if it doesn't belong in the area A. So the distribution of the point we obtain at the end is uniform only in the area A. Okay. So in order to perform rejection sampling, we have an area A. We find a bounding box around this area A. Then we sample a point uniformly in the bounding box around the area we want. We reject if it doesn't belong in the area A, and we keep and we repeat. Otherwise, if it belongs in the area A, we keep and we return. Okay? So let's do it now for the unit circle, unit disk, sorry. So we have the unit disk and we want to sample a point uniformly in the unit disk. So first thing to do, we draw a bounding box around the unit disk. Okay? So we choose this bounding box. We sample a point in this uniform in this bounding box. We know how to do this. We sample we sample two values from the random number generator, and then we scale them, as we've seen before. So we know how to draw a sample from the bounding box. And then we reject this point in the bounding box if it doesn't belong in the disk. So if x squared and y squared is higher than 1. Otherwise, we keep it. If x squared and y squared is less or equal than 1, we keep it and we return it. Okay? So this is the rejection sampling for the unit disk. And now last thing for today is how to choose the bounding box. Okay, we can choose this bounding box here, but we can also choose this bounding box here. So which is the best one, the correct one. Okay, both are bounding boxes around the area of interest from where we want to sample a point uniformly. Okay. So the first square, since this is the unit disk, the first square has side 2, this one. Okay, this is like tangent here, so it has side 2. The second square, we have chosen just a square that has side point 2.2. Okay, so both are correct squares in order to perform rejection sampling. So in both cases, we can sample a point in the square and then see if it belongs or not to the unit disk. However, we can choose which is the more efficient one by checking the number of iterations of the rejection sampling until it gives us a sample, okay, in the area we want. So as we said, the number of iterations is 1 over the probability that x and y will belong in the area of interest. So here that they will belong in the unit disk. So practically when x squared and y squared is higher, less or equal than 1. Okay, so when x comma y will belong in the unit disk. So it's not, we cannot see it here, but I will explain it. So in the first case, in the first square, the number of iterations becomes 4 over pi, because the probability here in the first square is pi over 4. Okay, so it's 1 over pi over 4, so it's 4 over pi. In the second square, the probability is the number of iterations is 1 over pi over 4.84. So the number of iterations becomes 4.84 over pi. Okay. Therefore, in the second case that we chosen the larger bounding box, the number of iterations is higher. So it is expected that in the first case, the rejection sampling will give us a random sample uniformly distributed in the area of interest faster. So it's more efficient. Okay, it's more efficient to use the smallest bounding box. So that's it for today. So if you have any questions, I would be happy to answer. No questions. Okay. Thank you very much, and see you tomorrow then.